Okay, I'll make a start. Welcome back, everyone. Today we are still doing infectious disease models, but we're moving on to some new types of models. So the last couple of lectures, we've been focusing on SIR models. Today we're going to be thinking about some variations on this. So we're still thinking in this compartmental model framework, where we split populations into different classes according to their disease status, but we'll be thinking about some slightly different disease scenarios today. So we'll learn a couple of biological terms. We'll talk a bit about endemicity. So this is when a disease is staying within a population, as opposed to an epidemic, which is more of a transient thing. And we'll talk about latent period. We've already discussed this a little bit. This is the time before an individual becomes infectious. We'll talk also about some next generation metrics as well today. Okay, so let's think about some generalizations. So like I said before, we've met this SIR model a couple of times now, where we had susceptible, infected, and also infectious individuals and recovered individuals. And in that model, after individuals recover from infection, they become fully and permanently immune. So they can't become reinfected again in future. Okay? But for some infectious diseases, recovery doesn't always lead to immunity. Sometimes when you recover, you immediately become susceptible again, or very quickly become susceptible again. This is especially true with various sexually transmitted infections, things like gonorrhea and chlamydia. There's no long-lasting immunity. Also, another sort of simplification in this type of model is that following infection, there was no latent period before becoming infectious. So you go from the S to the I class, and as soon as you're in that I class, you're just like anyone else in that infected class. So it doesn't matter whether you've been infected essentially for a minute or a week, you are as infectious as anyone else. Obviously, that's a simplification. We are going to consider today what happens if we have an exposed period before you. So you're infected, but you're not yet able to infect other people. So we're going to look at two variations on the model today. First, this SIS model. So where you go from susceptible to infected and then back to susceptible again, rather than being recovered and removed from the pool of susceptibles. And then also something called an SEIR model, where the E is exposed. So we'll look at these two variations on the model today. Okay, so let's start off with an SIS model. So visually, what's going on here, if we think about a transition diagram, individuals go from being susceptible to infected. So this is infection. Previously, we had an R class, but now recovery just leads you straight back to the S class again. So let's think about how we would change the model that we had before. Well, before, remember we had this minus beta SI term, assuming we've got density-dependent transmission. We had a DI/dt term, rate of change for our infected individuals. Here we had beta SI, so our new infections, minus gamma I, where gamma is our recovery rate, 1 over gamma is our average infectious period. And then previously we had a dr/dt equation, which was just equal to gamma I. But now, because recovery leads to susceptibility again, these individuals just end up back in my ds/dt equation. Yes?
Why do we not have any stochastic effects in this model? As in, like, before we had kind of like a parameter that kind of like the efficiency of one class.
Like in our predator-prey models?
Yeah, kind of like that. Would it also have that in this model, where it's kind of like,
I mean, you could definitely do stochastic versions of this model. In terms of efficiency, are you thinking of like people that are infected, like where are you thinking they would go?
Like I was thinking there'd be some like efficiency involved with becoming infected. Like,
I mean, effectively you can capture that in the beta term, right? Like that's just, this is we're talking about a homogeneous population, or, you know, this is an average effect across the population. So beta is essentially an average transmission rate. So there might be some stochastic variation in that. So some people might be more transmissible, more have a high transmission rate. Other people might be more susceptible or less susceptible. And people might have more contacts, fewer contacts. So this is essentially just an average across the population. Okay, so note here one thing, that ds dt is just equal to minus di dt. We'll come back to this right in a moment. Okay, so we worked out how we could non-dimensionalize the SIR model, basically do exactly the same thing with the SIS model if we allow U to be the proportion of hosts that are susceptible, and we rescale time according to the average infectious period 1 over gamma. Then du dt now becomes minus brackets r naught u minus 1, close brackets, times by v, and dv dt is just r naught u minus 1, close brackets, times by v. So we still have this principle that du is equal to minus dv dt. And as before, we've defined R naught to be our basic reproduction number, which is our transmission rate beta times by the population density n. We haven't actually defined n on the previous slide. The n was equal to s plus I. And gamma is our recovery rate. So just like before, we can non-dimensionalize the model. I've not gone through the step-by-step stages, but it's essentially the same as what we did previously. Okay, so again, we have du dt is equal to minus dv dt, just like on the previous slide, ds dt was equal to minus di dt. So what can you conclude about this system? Yeah.
I had a quick question with
Yes.
the previous slide.
Sure, go for it. Yeah.
We said that ds dt is equal to negative di dt.
Mm-hmm.
Oh, whoops. I didn't see the second term in the first one, so I was like, how is equal?
Yes. Okay.
Okay,
Good.
sorry.
Good. That's okay. Okay. So ordinarily, when we're doing these systems of ODEs, we have, say, a system of 2 ODEs. We would have 2 variables, and they would be completely independent, right? So in principle, if you're somewhere on the plane, let's do it on this one up here. If you're somewhere in the sorry, that's because I'm recording this. If you're somewhere on the SI plane, you could in principle be anywhere in this plane, right? We saw that when we had our SIR model, that because we were constrained by having this constant population size, you couldn't actually necessarily go anywhere in this plane. You were constrained to a simplex, a triangle, essentially, where there was this line down here, S plus I plus R would have to equal what, N. Likewise, in the rescale model, U plus V plus W is equal to 1. So there was a constraint here, right? So what can you tell me about the constraint here? So like how many equations do we need to actually solve? 1? Yeah, because as soon as we know U, we know V. So if we know the change in U, we know the change in V. Therefore, if we know U, we're going to also know V. So given that U plus V is going to equal 1, we can just do a simple substitution. So U is equal to 1 minus V. I could substitute V for U, but I'll do it this way around. So what do we have? Well, dv dt from the previous slide was equal to brackets R naught U minus 1 times by V. So if we make this substitution that U is equal to 1 minus V, we're going to get R naught times by 1 minus V minus 1 all times by V. Okay, so let's expand this out and do a little bit of rearranging. So one way to expand this is to have R naught V times by 1 minus V. So just expand the first term and then minus V, expand the second term. So it's pretty clear here that I've got 2 terms that are linear in V and then something that's quadratic in V. Yeah. So let's essentially group the linear terms and group the quadratic terms. So what I'm going to do first of all actually is I'm going to bring out a factor of R naught minus 1 for the linear terms. You have R naught minus 1 times by V. And we've got a minus R0 V squared. Well, these now both have a factor of V in them. So one thing I can do is I can take out a factor of R0 minus 1 times by V. So if I take out this factor of R0 minus 1 times by V for both of these terms, I'm going to have 1 here minus R0 V squared over R0 minus 1. So all I've done is I've taken out a factor of R0 minus 1V from both terms. Here there was no R0 minus 1. That's the thing that's confusing you. So because I'm multiplying now by R0 minus 1 on the outside, I have to divide by R0 minus 1 on the inside to make these balance. If you multiply this by this, R0 minus 1 is going to cancel here. I realize there shouldn't be a V squared. That should be a V. That might be why you're also looking a little bit confused. The V's here will give you your V squared. This will cancel with this, and we know the minus R0. Everyone, same page? Great. Okay, so let me rewrite this in a slightly different way. Well, R0 minus 1, R0's just a number. It's just a parameter. Mon's just a number. So I'm just going to write this as a lowercase r. Then we've got a V, and then we've got a 1 minus, well, this term here is linear in V. We've got R0 divided by R0 minus 1. R0 is just a number, so R0 divided by R0 minus 1 is just a number. I'm going to call that number 1 over K. What have we got? Logistic growth, right? Becoming a logistic growth model, right? So this is with, sorry, I keep doing this because it's in the bottom corner. There we go. Maybe if I move that up there. Okay. This is with R is equal to R0 minus 1 and K is equal to R0 minus 1 over R0 or 1 minus 1 over R0. So this is logistic growth, yeah.
Does this tie in any way with our consumer resource models? Because we also got logistic growth when we looked at that, right?
Yeah, definitely. I mean, the consumer resource thing kind of carries on to the ideas of hosts and pathogens, right? So we are, as hosts or potential hosts, we are resources for pathogens. So they are using our cells, our tissues, our organs to replicate. So we are a finite resource. In the context here, there's a balance in terms of depletion of the pool of susceptibles. So the pool of susceptibles is a resource, and that is getting depleted. It's getting replenished by recovery, but those rates ultimately balance, right? So this is telling us something about the rates at which individuals are becoming infected. This K, this carrying capacity, will depend on both rates of infection, that's our beta times by N, and our recovery, gamma. So it's going to depend on the balance between those things, right? We can also see here that if our R0 is bigger, our carrying capacity is larger. Yeah.
We're also assuming that people who get infected, they don't die.
Exactly. Yeah. So this is a simplified model, just like our SIR one from previously, where there's no host demographics either. So there's no births or deaths in the host population. We're kind of assuming it's a relatively short period over which this initial epidemic occurs. And we're also assuming, yes, that there's no deaths from disease. Okay, so we've got logistic growth. So let's then think about our equilibria and the stability. So because this is equivalent to our logistic growth model, what do we have? Well, we're going to have equilibria at U star B star equal to what? Can anyone tell me what are equilibria? We're going to have two equilibria, right? That should be a 0. Okay, so what are my two equilibria?
I was thinking 0, 0, and 0, K.
Okay, what would 0, 0 mean? Tell me what U star is. I'll tell you what, no, what is U? Keyword there, proportion. Okay, what is V? Proportion affected. Okay, so what would 0, 0 represent? Yeah, so because we're dealing with proportions here, and remember, if we go all the way back up here, when we did this rescaling with SIR model, we divided by N. So if there's no individuals in the population, we would be dividing by 0. So like I said, it's kind of outside of that. Because we're dealing with proportions, we have to assume that there is at least some proportion that is susceptible and or some proportion that is infected, right? So 0, 0 isn't an equilibrium of this model because there is no, well, it's an equilibrium, I guess, in the sense that if you set V is equal to 0, you always end up with an equilibrium. It's just things kind of break down and become meaningless then. It's true for any value of U. So our equilibria that we care about, in a sense, from our logistic growth model. So let's just go back to this model here. So let's think about it in terms of here. From this model here, what are our equilibria? So V is equal to K, yeah. So V is equal to K is one of our equilibria. What's our other equilibrium from our logistic growth model? Just from this equation here. dV dt is equal to 0 when either V is equal to K or V is equal to 0. Yeah, okay, so let's go from there. So V is equal to 0 or V is equal to K. Okay, what is K? We worked out K above. K is 1 minus 1 over R naught. So I can replace that here. 1 minus 1 over R naught. Okay, what do we know about U plus V? Is equal to 1? Yeah, sorry, I couldn't quite hear you. U plus V is equal to 1. So what's U star here? 1. And U star here? Yeah, so this is going to be 1, and this is just going to be 1 over R naught. Okay, so this is our disease-free equilibrium. And this is our endemic equilibrium. Remember as well from our stability of our logistic growth model that our endemic equilibrium, which I'll abbreviate to EE, is stable when lowercase r minus 1 is greater than 0. In other words, when R naught is greater than 1. So this is the same threshold. So this is saying when, remember we had this epidemic threshold in our previous model, in our SIR model, when the disease is able to spread, it will tend towards this endemic equilibrium. Once it gets there, it stays there. If R naught is less than 1, this endemic equilibrium is biologically unrealistic. And our disease-free equilibrium is locally asymptotically stable. So the disease dies out. So it's the same interpretation as before. It's just now we end up at, if the disease spreads, it tends towards this endemic equilibrium. So note here we have two equilibria rather than a line of equilibrium. So remember we had those phase planes from the last lecture where we had a line of equilibria along the bottom where V is equal to 0 gave us some values U and 1 minus U for our, where W is equal to 1 minus U. And we had 0 for V, and any point along that line was an equilibrium. Now we just have these two equilibria here, disease-free or endemic equilibrium. So we say, this idea of this, the reason it's called an endemic equilibrium, this is contrasting with the idea of an epidemic. That transient phase is an epidemic. And if it remains in a population, then we say that it's endemic. That's why we call it an endemic equilibrium. Any questions? Yep.
So I'm still a little bit confused as to how an endemic differs from an epidemic.
So endemic, it's a good question. So you can think of an epidemic as that transient dynamic, right? So we have like during the early stages of COVID, that was an epidemic, right? Because it was spreading through the population, things were dynamic. Typically, when we refer to things as being endemic, they're maintained over a long period of time. So this is where a little bit of like the sort of biological or public health definitions of endemicity might differ a little bit from how it's sometimes used as like mathematically. Just because something is endemic, it doesn't need to be at equilibrium. It's just sort of maintained in the population. So it could be oscillating, like, you know, we have seasonal flu. So flu is, influenza is endemic because it's maintained in the population, but it does oscillate because of seasonal dynamics. Okay, so we have these winter outbreaks. So there are winter epidemics, but overall it is endemic in the population. If you contrast that with something like Ebola outbreaks, an Ebola outbreak sort of like occurs and then it dies out. It's not maintained in the population at a sort of a normal level. Yeah. We also might see, you know, because of things like vaccination, there might be occasional measles epidemics, but measles is not endemic in the population. It's not maintained. Yeah. Okay, let's move on to the SEIR model. So I wanted to introduce this because I'm also going to go through something called the next generation matrix as well. And that takes a little bit of time. So that's why I'm going through this stuff a little bit quicker, just so we make sure we cover that. Okay, so let's think of this other variation on our SIR model where there is an exposed or latent class. You remember when I said this exposed class is individuals, which are referred to as being this E class, who are have been infected, but they are not yet infectious. So if they were to take their COVID test on their first day, they might test positive, but they're not necessarily able to infect anyone else yet. That's not necessarily true of something like COVID, but just giving an example of people maybe taking a test and finding out that they're infected, they've been exposed. So what does this look like? Well, we can have an SEIR model. So our transition diagram is just going to have this linear look to it. It's always useful in these compartmental models to, I think it's useful to do a quick sketch of what the transition diagram should look like, right? So there's a quiz this Friday where we're going to be dealing with a different type of model. Think a little bit about what the transition diagram looks like at first. Okay. So here, this first thing is exposure. We then have, I guess, what's a good way of, I don't want to introduce too many new terms to you guys. I'm going to say infectiousness is probably the best way to write this down. Infectiousness. So they become infectious, and then recovery. So what does our model look like? Well, we still start off with our same format for our DSDT equation. This is minus beta SI. We now have an exposed class. So individuals, once they become exposed, they go into this class minus beta SI. And we're going to assume that they leave this class at a rate sigma, per capita rate sigma. So we have minus sigma E. So 1 over sigma is going to be our average latent period. So just like our average infectious period, this is the expected time that individuals spend in this exposed but not infectious class. Yeah.
Could you think of sigma as a probability instead of a rate, or no?
Not necessarily, no. This sigma could take any positive value. So this could be, for example, 2, in which case it would be a probability. Yeah. One can create probabilistic models where you would have, say, a probability per day at which you would leave the exposed class. So you can create models that are phrased in terms of probabilities as opposed to rates. Yeah, but there would ultimately be some time-dependent thing there where I said like probability per day or probability per week that you would leave a class. Okay, DIDT now. These are individuals who are infected and infectious. Is going to be sigma E minus gamma I, where gamma is our recovery rate, and the RDT is just gamma I. Can anyone tell me if N is our total population size? What is dNdt? Zero, right? We will be meeting some models where this isn't necessarily true. So again, we're assuming there's no mortality to disease. If there was mortality to disease and nothing else in this model, this wouldn't be equal to zero, right? Because individuals will be dying. If there were births and deaths as well, we might not necessarily have this equal to zero. Okay. We can do the same kind of non-dimensionalization we've done before. Again, I'm not going to go through the details, but feel free to do this in your own time. We're going to rescale time now according to a scaled average latent period. So this is going to take into account both our recovery rate gamma and our time spent in the infected but not yet infectious exposed class, sigma. So our model now becomes minus R0 UV for du dt. I'm going to call X our proportion of the population that are exposed as R0. This changes according to R0 UX, sorry, R0 UV. R0 UV minus delta X, so delta is this scaled average latent period. dV dt is equal to delta X minus V, and dW dt is equal to V. Again, we could eliminate one of these because they were all sum to one. Okay, suppose, I said R0 here is our basic reproduction number again, but I haven't defined what this is. So we're kind of doing things a little bit back to front here. Previously, when we found our basic reproduction number, one of the ways we did this was essentially to solve our per capita rate in the change of infectiousness. So 1 over V times by dt. When is this positive? In other words, when is this greater than 0? Assuming that the whole population, in other words, assuming that the whole population is otherwise susceptible. So in other words, when U was approximately equal to 1. So this is how we solved this previously. This is just the same as saying 1 over I times by di dt. When is that positive? So when is the per capita growth rate, when rare, when is this positive? This, rearranging that, gives you your R0. Now, we can actually do this in this particular case. So what I'm about to show you is actually strictly not necessary for this particular model here. The reason being that there are no demographics here. So one thing we could do is we could just sum together our total number of infected individuals, or total proportion infected, which will encapsulate both individuals in this X class and in this V class. So if we sum these two together, the dx's are going to cancel, and we'll end up with R0 UV minus V. The model will look basically identical to what we had previously. Yeah, and this is just exactly the same as our SIR model. We've just not broken it down according to our exposed and infected classes in our SIR model. Here we've broken it down. This means that the R0 will be identical. So we already know this going in. okay? So just to make sure that's clear, if you were to add this and this together, let's call this Z, dz dt is just going to be R0 uv minus v. If you then take these three equations here, where Z is our total proportion infected, this is identical to the SIR model that we looked at before. Yeah, so the R0 is going to be the same. We already know that going in. However, let's just suppose we didn't know that. The reason we're going to do that is because I want to introduce something called the next generation matrix. So this isn't always true. The only reason this works in this case here is because there's no demography, so there's no change, or really there's no loss in this class here. So everyone that becomes exposed, eventually becomes infected. But what happens if some of these individuals were to recover before they become infectious, or die before they become infectious? Then your R0 is going to depend on how long they spend in here as well. So that means that our population is structured in such a way that we actually need to account for the contribution to new infections from this class here, as well as individuals who pass through this stage here. Don't worry if you haven't quite sort of grasped why that's important just now, but it basically means that we need to factor in contributions over the course, sort of the expected lifetime contributions from individuals that start off in this exposed class with not necessarily everyone making it to this infected class. Yeah.
Wouldn't our rates not check out if we sum them? Like unit-wise, if we sum like dxdt and dvdt, so we're referring to two different types of rates, right? So the units have to check out basically for having like.
I mean, the units should always check out anyway, right?
Yeah.
Like, and this is fine, right? I mean, this is a non-dimensionalized model anyway.
Yeah.
So R0 is just a number, and we've got a -1 in front of the v, and u and v are both proportions, and x is a proportion as well. So this equation here balances. There's no issues with units here. But as a general point, yes, one should always check units. Okay. So just to make sure it's clear what I'm kind of driving at here. If we can collapse our model down in the way that I've written here, then it's equivalent, it's exactly the same as our SIR model. So if we want to find R0, we can just look at the per capita growth rate when rare, see when this is positive, rearrange to get us a quantity R0. Okay. However, if you can't write it in this format, you have to account for the contributions that will occur from individuals who go through this exposed class to new infections, as well as individuals who eventually make it into this class here. Basically, the population is structured, and we need to account for that structuring. The way we do that is through something called the next generation matrix. We use this typically when there are multiple infected classes. You might also want to do this in other scenarios, say when individuals, let's take something like sexually transmitted infections. That's a particularly good example. You might have individuals who have a low sexual contact rate and individuals who have a high sexual contact rate. So you maybe have low risk and high risk populations. They will have different contributions to the spread of sexually transmitted infections. So in particular, for sex workers might be a particularly high risk group. And therefore, often in models of sexually transmitted infections, there is some breakdown according to risk, because people disproportionately contribute to the spread of sexually transmitted infections depending on their the nature of their sexual contact network. So you have to account for those differences if you're going to find R0. Okay, so the same principles apply. We're doing it in a very simple example here in this SEIR model where it doesn't matter, but in general it does. So what are we actually going to do? Okay, so I'm not going to go through the sort of linear algebra behind why this works. This is something I'm going to say take on faith. You both took the math evolution course, so you're familiar with the next generation matrix, but we run through this in a little bit more detail. This is just the headlines, okay? So suppose we have a Jacobian matrix J. In fact, if we have any matrix, there is something called the next generation matrix, which is given by the product of two matrices, F and V inverse, where we define these two matrices, F and V inverse, from our Jacobian. So J is equal to F minus V. Might seem a little bit strange as to why we're doing that, but it's basically, it gives us a neat linear algebra trick, which allows us to a relatively straightforward way to calculate R naught. We could calculate this from the Jacobian, but it's generally easier doing this from the next generation matrix. The way that we construct these F and V matrices is very important, though. There are some rules around how we do that. For the purposes of what we're doing with these infectious disease models, the very simple interpretation for F is this F matrix only contains terms from our model that correspond to new infections. So we write down our Jacobian, and then from that Jacobian, we look at each of the terms that are in that Jacobian, and we pull out only the ones that correspond to new infections. Everything else we set to 0. V is then just determined ultimately as this is actually defined as all movement between classes and also loss from J. So loss here in the infectious disease context can mean recovery, death, things like that. Movement between classes might be, say, going from the exposed to the infectious class, things like that. So why does this matter? Well, it can be shown, like I said, we're not going to go into the mathematical details behind this, kind of beyond this course, but our basic reproduction number is given by the eigenvalue of this new matrix, F times by V inverse, that has the largest absolute value. This is also known as the spectral radius. So sometimes it can be difficult, especially if we had many, many different classes, to find what that R naught is. However, often you have very few new infectious terms in your model, and you have lots and lots of zeros, therefore, in this F matrix. So when you multiply F by V inverse, you end up with a matrix that has lots and lots of zeros in it. Often this is in triangular or upper diagonal form. Often it's very, very easy to just read off the eigenvalues. And so it's typically much easier to translate this problem into this next generation matrix because you can read off your eigenvalues. Yes?
Are we given F and V, or do we have?
So that's what we have to work out. We have to work out what F and V are. So I'll go through an example of how we write those down now. Okay. Incidentally, just so you guys don't panic too much, there won't be any next generation matrix stuff in the quiz on Friday. Okay. We'll be going through this again in a bit more in future lectures, but don't worry about this for the quiz on Friday. Okay. Okay. So let's go through our SEIR model. So if we think about our Jacobian, this is a 4D model. So I'm just going to write down the SEIRs here, just so it's clear what's in each of these columns and rows. Now, I'm not going to care about what happens in any row or column that has S in or R in. The reason being is because this is all about new infections being produced. So I only care about flow into my infected classes. So what are my infected classes? E and I. So immediately reducing this down to a smaller problem with just 2 classes. So what's my Jacobian here? Well, with respect to E, I, and R, well, I realize at this point I've gone back to my, I've essentially in the notes, I've gone back to my my dimensional model. Okay, so a little bit back and forth here. I should have probably done this in terms of my non-dimensionalized model, but we've gone back to this format here with our betas, our sigmas, and gammas. Okay. So if we calculate our Jacobian, all of these terms are linear in each of these variables. So it's pretty straightforward to write down what this Jacobian is. We'll end up with minus sigma, beta s, sigma, and minus gamma. So this is like a sub-Jacobian. And recall, the reason we don't care about the S columns, the R columns, and rows is because we are trying to find an R naught, which is telling us about the growth of infections. As an aside, really what we're doing here is we're actually seeing what is the stability of our disease-free equilibrium. R naught is telling us when R naught is greater than 1, that tells us when our disease-free equilibrium is unstable. So our disease-free equilibrium could have any values of S and R. Typically, S would be equal to the total population size and R would be equal to 0. And so we're seeing when is that stable. So we already know that in the absence of disease, that will be stable. So we're looking at this submatrix here, because this submatrix here is going to tell us when the epidemic is going to be able to take off. Okay, the eigenvalues of this, if they have real positive parts, then we know that our disease-free equilibrium is not going to be stable. So that's where we're going. Okay, so from this, what do we get? Remember, J is equal to F minus V. And what was our F matrix? Well, our F matrix we define as a matrix that contains all new infectious terms. So anything that's to do with new infections. So let's go through these matrices here. I've called this J over here. I'm actually going to rephrase this a little bit. I'm going to call this J naught. And then this thing inside is just our submatrix J. So this 2 by 2 matrix here is our J. Okay. So what are our new terms referring to infections? Well, this sigma, remember sigma, this is where you have to kind of go through and think about the biological meaning behind each of your terms. Sigma, what was that in our original model? Well, sigma was all about movement from being exposed to being infectious. Is that a new infection, though? No. New infections are only things coming into this term here. They have become infectious, but they're still infected. If we think of the total number of infected individuals is E plus I, if they subtract one individual from the E class and add them to the I class, you still have the same number of infected individuals, right? So sigma has nothing to do with new infections. So both this term and this term are equal to 0 because there's no new infections here. What was gamma?
Recovery rate?
Recovery. Is that new infections? That's 0. Beta S. Beta is our transmission rate, right? So this is a term that deals with new infections, beta S. If there were other things in here, suppose, for example, there's a beta S plus, I don't know, epsilon something, whatever. If that has nothing to do with infections, we would leave that there. We only take out the actual term itself, not the whole thing that's necessarily there, just the term that we care about. Okay, so then what's my V? Well, my V is just going to be it's just going to be F minus J. So this is going to be sigma 0 minus sigma gamma. Okay, let's work out my F times by V and my next generation matrix. Well, it's going to be the product of these two matrices where we take our V inverse. So F is as it was above. My V inverse, remember how to do the inverse of a 2 by 2 matrix? I remember how to do it. We flip these terms around here, exchange these terms, change the signs of the ones on the off diagonal, and then divide by the determinant. If you do all of that, a little bit trust me algebra here because I don't want to spend time working out 2 by 2 determinants in class. But you get 1 over sigma, 0, 1 over gamma, 1 over gamma. Okay, so now we need to take the product of these two matrices. If you do that, you're going to get beta S over sigma, beta S over sigma, 0, 0. Cool, what we said on this previous slide. our basic reproduction number is given by the spectral radius of this next generation matrix, the largest eigenvalue. The eigenvalue of the largest absolute value, which in this case is always going to be positive anyway. So this is in a triangular form, right? This one's 0, this one's beta s over sigma. I don't have to do any more calculations here. I can just read off my eigenvalues straight away. So R0 is going to equal beta s over sigma, or beta n over sigma. Sorry, gamma. I've written these down as sigmas. These should all be over gammas. The reason is because S is approximately equal to N at our disease-free equilibrium. So note that this, as we concluded before we even did any of this, that our R0 in our SEIR model here without demography and without disease deaths is exactly the same as it was in our SIR model because there's no loss of terms. Okay, so this was just to demonstrate that we end up with the same thing. In general, that's not going to be true though. Okay, so if we had some loss from our exposed class, and we'll deal with this in some future lectures, if we had loss from our exposed class, we wouldn't be able to do this method up here, where we just sum the classes together and find the per capita growth rate and rare. We'd have to use the next generation matrix, and that's where it becomes powerful. So typically, this is the approach that we would take when we have this, our population structured over multiple infectious classes. Okay. So just wanted to emphasize that while we've ended up with the same thing here, that's not true in general. Like I said, this is not going to appear in the quiz on Friday. We will be doing more with the next generation matrix. This is just an introduction to it. Don't worry if you don't quite get this just yet. We'll be recapping this. And I recapped this in the last lecture of the course as well, just to go over it. This is pretty in some ways, technically one of the more complicated things in the course is to understand this process. I've not gone into the linear algebra behind it. If you want to, you can. There is a reference to this paper here, which deals with this if you really want to. I can also give another reference if you want to go and read the papers behind this. This is all essentially about the reason we do this problem is it translates the problem in such a way that when we biologically define these F and V matrices in sensible ways, okay, this is all about new infections, then typically we end up with a scenario like this where our F matrix has lots and lots of zeros. Then when we take the product of these two matrices, we can usually immediately read off our eigenvalues, and therefore we can immediately find out. So it is essentially a mathematical trick, a linear algebra trick, to quickly find R0 in models where we have lots and lots of infected classes. Yes?
We computed J at the disease-free equilibrium, right?
Yes, yeah. That's why this S goes to N here. So I could have set this here at J star with this S is equal to N, rather than doing it at the end. I left it in its most general form, but yes, that's what we're doing. And the reason we're doing that is because remember I said here, what we're really doing is looking at when is our disease-free equilibrium unstable. For our disease-free equilibrium to be unstable, we need the eigenvalues of this submatrix here to have real positive parts. The linear algebra trick is basically saying that is only true when the spectral radius of this next generation matrix is greater than 1. We define our R0 at this threshold of 1. Therefore, that's why we end up with this eigenvalue here. When this is greater than 1, that implies that the eigenvalues of this submatrix here have real positive path. That's kind of the math that's going on behind this. R0 greater than 1 here implies this submatrix here has real positive eigenvalues. Therefore, our disease-free equilibrium is unstable. I'm seeing a few confused faces, which is fine. We'll be recapping this and applying it to models where we have high and low risk populations and seeing also in models with demography why it matters. Okay, so again, don't worry about if you haven't quite understood this now, it's not going to be examined on Friday. Okay, that is about time. Any questions before we go? Okay, there is some code on Canvas to explore how varying the models that we've met so far affects the dynamics. You can see how, say, varying the transmission rate or varying the recovery rate, ultimately varying R naught affects the kinds of peaks that we see, the kinds of epidemic dynamics or endemic dynamics that we see. Yeah. Okay, see you guys on Friday. Same rules as before for the quiz. Okay, so it is open book. I would encourage you to look at your notes as well during the quiz, and it will be about disease models, but not about next generation stuff. Okay.